This section's about vector fields, and we're going to start with the velocity vector field. Right here, we see the air velocity vectors that indicate wind speed and direction at points 10 meters above the surface elevation in the San Francisco Bay Area. And you see at first fall to glance, you can see that the yellow is the greatest wind speed at the time, and it occurred as the winds entered the bay from the Golden Gate Bridge. And then the second figure, part B, shows 12 hours earlier, and it's very, very different, but you can see where the wind is going. So these are velocity vector fields. These next two figures are also velocity vector fields, and they are ocean currents off of Nova Scotia and airflow past an inclined airfoil. So another type of vector field we're going to look at, called a force field, indicates the force with each point in the region, and we're going to look at those as well. But in general, a vector field is a function whose domain is the set of all points in R2 or R3, and the range is a set of vectors. So we have a definition. It says, let D be a set in R2 which is a plane, and then a vector field on R2 is a function f that assigns each point x, y in D a two-dimensional vector. I'm going to say a 2D vector just to keep from writing it all out. A two-dimensional vector f of, this is a bold f, f of x, y. So f is a vector, and then we have a vector field. So the best way to picture a vector field is we draw arrows representing vectors for f of xy, starting at the point xy. And it's impossible to do it for all of them, but you can form a reasonable impression of f by drawing vectors for a few of them. You can see this in this figure for figure 3. And since f is a two-dimensional vector, you can write it in terms of its components. So we call them p and q. So generally you're going to have a function f of xy is equal to p of xyi, and this is our vector I, plus q of xy, and this will be in terms of j. And if you hit if you hit a three-dimensional, then you would have plus another one for your k, and we can write this as a vector p of xy and q of xy. So we can say that f is equal to p times pi plus qj. So that's our notation going there. Notice that p and q are scalar functions. They're sometimes called scalar fields to separate them out from vector fields. So since they are scalar functions, we sometimes call them scalar fields. So we have another definition, and it says, definition, I think the pink works. For some reason, my marker doesn't work. The pen doesn't write anymore. It's very fat, and it doesn't work. So I'm going to try to get that figured out soon. Let's let E be a subset of R3. Then a vector field on R3. So it's very similar to R2, but we might as well talk about it. A vector field on R3 is a function f that assigns each point xyz in E a three-dimensional vector f of xyz. So similar to the ones above, we would add, let's come up here and let's say we would add plus r of, oh, we can't do that because those are xy and we need xyz. So let's come back down here and say f of xyz is equal to p of xyz times I plus q of xyz, and we have j, plus r of xyz, and we have k. So we're back to our vectors, and that could be good, that could be bad, and we could still write them like the one above in terms of pi plus qj plus rk. So just like we did back in chapter 13, we have vector fields. We can show that f is continuous if each of its components is continuous. And we sometimes identify a point with its position vector and write f of x instead of f of xyz. So so sometimes we'll use the notation f of x instead of f of xyz. And when that happens, we say that f becomes a function that assigns a vector f of x to the vector x. Anyway, just interesting notation, but the two definitions you need is your vector field on R3 and your vector field on R2. So let's look at an example. Before we get into the example, the good news is you are going to sketch them, but in WebAssign you're going to match them, so it's not too bad. So this example says a vector field on R2 is defined by f of xy equals negative y times the vector I plus x vector j. Describe f by sketching some of the vectors on f of xy as previously seen. So it's important that we have our f. I'm going to rewrite it down here. So we have f of xy is defined to be negative y vector I plus x vector j. And so what we need to do is we need to create a table of when you have xy, what the vector looks like. So this would be the point xy, and this would be the vector of f of xy. Now remember, these are vectors in the second part, so we're going to draw them as such and label them as such. I'm going to draw an xy graph over here. So here's my x and here's my y. And let's start with the point 1, 0. So when we look at the point 1, 0, we take the y value to be negative, and that's just going to be 0, so it's going to be gone. And then the x value goes with j, so we just have the vector 0, 1. So the way that we draw the vector field is we're going to start at the point that we chose, which is 1, 0 right here. And we're going to draw the vector 0, 1. That means we don't go left or right, because we go left or right 0 and we go up 1. So we have this vector right here. Now for my next point, I'm going to pick 2, 2. The first reason is I'm staying in the first quadrant and I'm moving away from that vector that we just drew. And the second reason is that's what they picked, so I'm going to follow suit. That may not be what they picked next, but I'm still going to do it. So we're going to change the sign of y, and then we're going to keep the sign of x. And we start at the chosen point 2, 2, and then we're going to draw the vector that we got, which means we're going to go 2 to the left and then up 2. We're going to draw that vector in. So there's that vector. And then let's do the point 3, 0. So when we do the point 3, 0, the y value is still 0, and the x value is 3. So we're going to start at the point 3, 0 down here, and we're going to go up 3 for our vector. So you can see it's not that hard to do. It's just a little tedious. Let's pick up on 0, 1. When we do 0, 1, we end up with negative 1, 0. So we're going to start here. We're going to start at 0, 1. Let me switch colors Let's do it in blue. So we have 0, 1, which means we have the vector negative 1, 0. And just so that you can see where this is going, I didn't label and draw my hash marks in. So let me go back and do that. So we have 1, 0, so we're going to start, 0, 1, we're going to start up here on the y-axis, 0, 1, and we're going to go negative 1 to the left in the x, negative 1 in the x direction and 0 in the y direction. So now we're basically doing the same points. So we're doing negative 2, positive 2 in the second quadrant. So that means we have negative 2, negative 2. So we're going to start at negative 2, positive 2. That's this point here. And we're going to go 2 to the left and then down 2. So that puts us down here for this vector. So now we're going to choose the point 0, 3. There's no method to the madness. You just kind of need to choose some so you can be able to build your vector fields. So we're going to have negative 3 and 0. So we're going to come up here to 0, 3 on the y-axis, and we're going to go 3 spaces to the left for our vector. So we could actually label it, this is f of 0, 3. So let's move into the next quadrant, and I'm going to switch over to this side. I'm going to label my axis xy and f of xy. So I'm going to switch them to be negative 1, 0. So when we do, remember that f of xy is equal to negative yi plus xj. So we're going to have 0, positive 1. So negative 1, 0 is here. And we're going to go negative 1, 0. Oh, there should be a negative 1 on there. I wondered what was wrong with it. Negative 1 down, and we have this happening. Now we can do negative 2, negative 2. So that will be positive 2, negative 2. So when we start at negative 2 down here, we're going to go 2 to the right and then up. Let's see, 2 to the right and then down 2. That's the way we're going to go, down 2. And then we have negative 3, 0. So when we switch them, we have 0 and then negative 3 still. So we're going to go to 0, negative 3, which is this point here. And we're going to go down 3 for our vector. This vector field makes no rhyme or reason. Most of the time they do, so you can kind of figure out what's going on in that case. And then let's pull in, maybe this color will be okay. And we're going to use 0, negative 1. So we have 1, 0. So 0, negative 1 is here. And we're going to go to the right one. You can see that these kind of made a box around a circle. You can kind of see that happening, but the circle is not part of the graph. But if I erase it, you won't see it at all, so I'm going to leave it there. And then we're going to do positive 2, negative 2. Notice how we did pick the same kind of points in all 4 quadrants, so that kind of helps you develop a pattern. So positive 2, positive 2. We're going to start at 2, negative 2, which is down here. We're going to, oh, that's 3. You couldn't see it because I had to erase it. And we're going to go up 2 and over 2 to here. And then the last one we have is 0, negative 3. And so when we find f of xy, we get 3, 0. So we're starting down here at 0, negative 3. And we're going over 3, 0. So it kind of does create a pattern. As you can see, it looks like it's traveling clockwise. It appears that each arrow in the center is tangent to a circle at the center, and we talked about that. So we could confirm it with a dot product, and we could work with the perpendicular knowing what we know. But we've done all that, so let's look at more. It says the book says some graphing software is capable of plotting these. WebAssign is going to give them to you to choose. You just need to be able to do enough to actually see them happen. But let's look at a couple of these. Here we have some vector fields that we could look at. Some graphing software is capable of plotting these in 2 or 3 dimensions. So look at the first one. It's f of xy is equal to the vector negative yx. That's what we have. Notice it's traveling kind of in a circle counterclockwise. Figure 7 is f of xy equals y sine x, the vector y sine x, and it's got some interesting patterns to it. And then figure 8 is f of xy equals the vector natural log of 1 plus y squared and natural log of 1 plus x squared. And all of that is moving towards the top right. You can see how it kind of forms a pattern. So that's your goal with the vector field, is to show what's happening with the vectors. And you can see that in figure 8, some of them are longer. So the farther you get from the origin, the longer they are. And that happens in figure 6 and 7 as well. And so those are patterns that we notice and talk about. We could see it when we did it in our last screen, that the larger the numbers we picked, the longer the vectors were. So let's look at this next problem. So this example says sketch the vector field on R3 given by f of xyz equals zk. So I'm only going to pick a couple problems in each quadrant, a couple points in each quadrant. So we have xyz, and I'm not going to write f of xyz. I guess I will, f of xyz, but what's important to me is that it's equal to zk. So I don't have to keep looking up. I can use my chart here. So let's start with, first of all, we're sketching in 3D, so that makes it a little more difficult. We can handle it. We got this. The point 0, 0, 0 is not helpful, so because it doesn't have a length. And then if we pick the point 1, 0, 0 or 0, 1, 0, let's do it, 1, 0, 0, then we have the vector 0, 0, 0. So that's not helpful either. So let's start with 1, 1, 1. If we start with 1, 1, 1, then we have a vector of 0, 0, 1. So here I've graphed the vector starting at 1, 1, 1 and going one direction in the z. So it goes up to 2. So then let's talk about if we have the vector, let's say 2, 1, 1. It's going to be beside the other one, and it's going to go up 1 as well. And you can see how 3, 1, 1 would do the same thing, and 4, 1, 1 would do the same thing, and negative 1, 1, 1 would do the same thing. It would be back, it would probably be back here. And then let's say that we went to So you can see how each of these vectors start at a point and they go exactly up or down a length, a certain z length, and that's because the vector is defined to be zk. So this one isn't actually too bad to do, but some of them can be very complicated. The one we did on the previous screen is not too bad because it's pretty simple to sketch by hand. So here we have figures in 10, 11, and 12. Figure 10 is y, I, z, j, and xk. And figure 11 is yi minus 2j plus xk. So we threw a constant in there so you can see how it took some of that craziness kind of, so to speak, out of it. And then figure 12 is an interesting one as well. So if figure 12 represents a velocity field, the particle would be swept upward and would spiral around the z-axis, as you can see from above, kind of. Imagine a fluid flowing steadily along a pipe and let v of xyz be the velocity vector at a point xyz. Then v assigns a vector to each point in a certain domain E, the interior of the pipe. So v is a vector field on R3 called a velocity field. A possible velocity field is illustrated in the figure, and the speed at any given point is indicated by the length of the arrows, so the longer the arrow, the faster it goes. Velocity fields also occur in other areas of physics. For example, the vector field in example 1 could be used as a velocity field describing the counterclockwise rotation of the wheel. So we saw other velocity fields in the problems that we've done. So we've talked about vector fields. So if you look at figure 14 is a gravitational force field. So it comes from working with Newton's law of gravitation. So it's just another one you can look into. We have an example that talks about an electric charge located at the origin. According to Coulomb's law, the electric force F exerted by the charge located at a point with a position vector given is that. Epsilon is a constant, and it depends upon your units used, and it goes on to all of that. So both fields are examples of force fields, but E is considered an electric field when that happens. Just so that you know, there are vector fields, there are gravitational fields, there are force fields, there are electric fields. Force fields feels like we should be somewhere else, but let's go on with that. So we have all of those other fields. We also have gradient fields. So think about the gradient that we learned back in chapter 14. The gradient of xy, the gradient of f of xy, is the partial derivative of with respect to x of xy I plus the partial derivative of y with respect to xy j. I got distracted for a second because this is really a vector field on R2. So let's say it's a vector field on R2, and that ties into what we're learning in this section. And it's called a gradient vector field. So we can call it specifically a gradient vector field. So when you're asked to find the gradient vector field, you already know how. You just got to put the proper name on it now. We can also find our gradient of f in 3 variables. So your partial derivative with respect to x, with I, your partial derivative with respect to y, with j, and your partial derivative with respect to z, and it will be with k. So it's still your gradient vector field, and nothing that we've done has changed. But now we know how to do our gradient field, and it kind of compares to a contour map. So in this example, we're supposed to find the gradient vector field of f of xy equal to x squared y minus y to the third. Plot the vector field together with contour maps. So remember that WebAssign is going to let you match, so it's not too bad. So we're going to say the gradient of f is equal to the partial of f with respect to xi plus the partial of f with respect to yj. So we're going to say the gradient of f is equal to the partial with respect to x would be 2xy, and the partial with respect to the partial with respect to y is x squared minus 3y squared. And you can write that in your IJ notation if you'd like. I tend to like my vector notation, so I'm going to leave it like that. Now let's look at the map. So if we were to plot the vector field, we would come up with this. So it shows our contour map with the gradient vector field. You can see that the gradient vectors are perpendicular to the level curves, which you would expect from what we learned in chapter 14. And notice that your gradient vectors are longer where the level curves are close to each other, and short where the curves are further apart. That's because the length of the gradient vector is the value of the directional derivative of f, and closely spaced level curves indicate a steep graph. So it kind of ties it all together. You have several gradients to do in your homework, but you understand the gradient and you understand the vector fields, so I think you should be okay. Before we do one more like your homework, it says a vector field f is called a conservative vector field if it's the gradient of some scalar function. For example, there exists a function f such that the force vector is equal to the gradient of f. In this situation, your function f is called a potential function for f. And they give you an example down here. Not all vector fields are conservative, but such fields do arise frequently in physics. So you can look through that. We're going to talk about it more later in chapter 16. But I wanted you to get a preview for it, and then we're going to do one more from your homework. A particle moves in a velocity field v of xy equal to the force to the vector x squared x plus y squared. If it is at position 2, 1 at time t equals 3, estimate its location at time t equals 3.01. So we know that we have a position 2, 1. Let's start there. So we have a velocity at 2, 1, which is equal to the vector x squared. So 2 squared is 4, and 2 plus 1 squared is 3. Now, this is when t equals 3. So when t equals 3.01, the amount of change we have is 0.01 units of time. That's our amount of change. So what we're going to do is figure out how much that is in the vector. So we're going to take 0.01 and multiply it times the vector of 2, 1. And that means we're going to take 0.01 times 4, 3. So what that does is that's going to tell us how much change has occurred in that amount of time change. So when we multiply this, we get 0.04 and 0.03. Now, that tells us that that's how much change we've had in the vector. So that means our position is going to change from 2.1 from 2.1 to 2.04 and 1.03. So that is the estimated location at t equals 3.01. It's not very difficult. It's just a little interesting, and it's an interesting twist on what we're looking at with these velocity vectors. I hope that you understand, and I hope that you have a great day.